Opened up the STL file. This mesh package consists of thousands of separate meshes, and these are separated along with the edge count. So that means that if I explode this mesh is going to be exploded into thousands of separate meshes. The first thing that I should do is that I should weld the mesh. Instead of having that high number of meshes, then I have only one mesh. So all those bold lines disappeared because I weld those joints. Normally, when you export a mesh that you want to import into Rhino for a flattening process, that mesh should be exported into an OBJ format. Those sort of problems are avoided. This mesh boundary is not entirely smooth. Overall, it looks good. It looks optimized, but there are small spikes at the boundary. The first thing that I want to do with this mesh is to go ahead and use one of the mesh tools that come along with the ExactFlat software. So I'm going to use the uniform remesher. But before doing that, I'm just going to save a backup of this mesh. So I'm going to change this object name and click mesh. I can duplicate the layer and objects. So it's going to be called mesh backup. I'm going to hide it. So now I can keep backups within my layers. And now I can work with this mesh separately. When I finish the process, I'm going to compare the final result with the squish command. When using the adaptive remesher, the uniform remesher, sorry, for this sort of meshes, what I'm trying to do is that I'm trying to smooth out the mesh. Normally, if you do provide a smooth mesh scan data, this should not be necessary. So this process may take some time. Basically, when remeshing, I'm seeing that I have a very high initial vertex count. So I'm gonna pick a number that's close to that right now. If the vertex count is still high, because my intention with this remeshing tool is to remove the inconsistencies along the edges. Overall, the triangle size looks pretty much even, and this is going to make it even more even. When I start the process, this might take a couple of minutes. Basically, what this is doing right now is that it is inflating the vertex count. After inflating that number, it's going to start reducing it back to the desired vertex count. Normally, when working with this, scan meshes, they come dense from the scanning software. They usually come a little bit dense. It's a normal procedure to remesh these meshes with some of our remeshing tools. If the boundaries were smooth enough, I wouldn't be using the uniform remesher, and I would normally use the adaptive remesher. What we're seeing right now is that now that we have inflated vertex count, it's going to reduce it back to 12,000, which is the input number that I introduced. And we can see now that the distribution of triangles, it's more even. We don't have sudden changes of triangle size. Also, the boundaries have been smoothed out too. If the mesh was smooth enough, then I would use the adaptive remesher directly, which is the tool that I'm going to use next. Basically, the adaptive remesher, what it is going to do is that it's going to smartly reduce the triangle count, and it's going to use bigger triangulation where you have more flat areas where within a tolerance those triangles can cover a bigger portion of the geometry. In order to optimize this patterns during the flattening process so that the flattening process works more accurately, this remeshing has to be done. probably to reduce the vertex count. So that's going to make our flattening process much faster. So I'm going to hit OK. Basically, I can see that all the features in this mesh has been preserved. The mesh has been smoothed out. And I don't see any inconsistencies in the boundaries. So now that my mesh has been smoothed out, I can use the adaptive remesher. Right now, I'm gonna try and see what results do I get with this default values. These default values are only calculating the overall size, and they're based on those dimensions. So basically what I'm seeing right now is that I'm losing a lot of the features of the original mesh. So I'm going to reduce the tolerance to some values that I think that will preserve those features, and at the same time will give me a more a reduced triangulation for the overall geometry. So for the desired surface tolerance, I'm going to pick 0.5 millimeters. If this is millimeters, I believe, then I will pick the desired boundary tolerance of 1 millimeter. I can try that out and see what happens. And the minimum edge length has to match the lowest of the two. So basically this is 0.5. I'm gonna start this command. This is telling me that I'm getting a high vertex count, but this will pop up whenever I exceed this number by 1,000. Whenever I exceed 1,000 vertices in my estimated vertex count. So I'm going to continue. Okay, so what I can see right now is that the features have been preserved, and I have bigger triangles where there's no need of having such a high amount of triangle. Before using this command, I'm gonna remember these values. I want to take this and basically duplicate the mesh and layer and objects just so I can keep another backup. Let's just try it again. I use these values right here. And for example, if I want to keep those boundaries more tight, I can use 0.5, the three of them. I don't see that they're producing a really high increase in the estimated vertices count, so I'm going to leave it like that. I'm gonna hit OK. So now that my mesh has been remeshed, now it's prepared for flattening. Now that I got this mesh, I'm gonna go ahead with my tools. Basically, start the flattening process, the flattening command. Now that I can see that 2 new layers have been generated, so I'm gonna stay and select the ExactFlat pattern. I'm gonna hide out my old mesh, and what this is going to tell me the level of strain and sag this pattern is suffering. I'm gonna go ahead to my top view and turn on my shaded viewport mode so I can see this. So basically, the flattening process consists of 2 stages. So the first step is to use one of the pre-flatteners. This mesh, what you're seeing, is not a proper pattern piece yet. This is only a projection of the original mesh, similar to the squish command or something. I mean, the way it's processing this, if this mesh was folding over itself, I would see folding and flip triangles being underneath. So in order to eliminate that flip triangulation and anomalies, we have to use one of our preflatteners. These tools are right here. We can use these preflatteners in any order we want and as many times we want. So basically, now that I have used this smart fracture preflattener, this has expanded the mesh in order to avoid having any triangles or folds or angles flipping and being underneath. Now that this has been pre-flattened, now I can go ahead to my second stage of my flattening process. So now I'm gonna use the optimizer. I'm gonna select my pattern piece, and what this is going to do is that it is going to calculate the geometry that the flat pattern should have in order to reduce the strain and sag as much as possible. So now what you're seeing is that whenever you see white, that means that part of the surface has a 0% strain. Cyan would mean that at that spot we're having 5% strain. Green will mean 10% strain, yellow 15% strain, and red will mean 20% strain or more. The optimizer will also calculate the material behavior. So you can pick any material from this library, and this is going to introduce those values into the calculation. If the material you want to use is not in this list, you can send a sample of the material. We have an agreement with the university, so you can send them a sample of your material, and that material will be measured up. So you can introduce those values and add that material to the material library. So basically I'm gonna select cotton. As for this example, it's going to be enough. And I'm going to hit the OK button here. And right now, this is going to expand the material and calculate which shape it should be in order to be applied to that 3D surface. So you'll see how the strain and sag are being reduced, so we don't have cyan any longer along the pattern. And we can also measure the level of the average energy density we're having. That means that compared to the energy density of 1% elongation, which is a fixed rate depending on the material, we can notice that we're having an average energy density below 1%, and I would say that's even below 0.001%. So that's a really low level of strain. Another value that we can look at is the no-seam stretch error. Basically, the no-seam stretch error is the difference between the overall circumference or perimeter of the flat pattern compared to the original perimeter of the surface, which is of 3200 inches. That's really low too. In case you want to even constrain this boundary even more, we can adjust those parameters during the optimization process, but in expense you'll have more stretching. Your material will have more strain, because if you reduce all the boundary perimeter, you'll be generating more strain when applying that pattern. If you want to do that, normally for mill protection, that's something that some people want to achieve, so we can re-optimize it and we can pick the preserve boundaries option. So my material, when flattened, when my pattern piece is not getting that much of expansion, and I can reduce the no-seam stretch tolerance for, let's say, 5 millimeters, for example. When I hit OK, and basically what we will see right here is that this is going to recalculate my pattern. So we'll still have really low average energy density, and we'll have a lower no-seam stretch error. In this case, it was of 7 inches, and now it's going to start reducing that number until it gets to the desired tolerance. In expense, we'll see that the average energy density is increasing. And that's a normal procedure because we are shrinking the overall perimeter so it matches the original perimeter. Depending on your material, if your material is elastic enough, in some cases you may want your material to be stretched, but that will depend on the workflow you're using. Basically, we have reduced the no-seam stretch error, so the overall perimeter has been reduced. There's our parent piece. We can see some cyan there. Those are going to be the stretched areas. We can compare this with the Squish command's result and see what happens. So basically, I'm going to open up my mesh backup, which was the original mesh. And I'm gonna run the Squish command. Or to see what results do I get. There you go. I'm gonna open my ExactFlat pattern here, go ahead to my top view and compare both results here. We can see that they are not the same pattern. The Squish command won't accurately represent an accurate flattened representation of the pattern. So we can see where we get more curvature, like on this top area, we are starting to lose some of the desired shape. And this is an accurate calculation that you can set up. You can play with the strain levels. We can add grain lines. We can add different tags, features. We can project lines and features to my 3D model. So those features and those tracing lines get flattened too. And we can play with our optimizer values in order to get different levels of strain and boundary constraints. So once I'm done, I can, let's just hide everything up. Once I'm done, I can export a DXF file. This is going to be flat pattern. And once you get your DXF exported, you can import it back to Rhino and check it out. Okay, so in this case, we're working with millimeters, if I'm not wrong. So, sorry, in inches, if I'm not wrong. So that's it. Basically, what you're getting now is a curves file. This file can the output of this DXF can be set up through the options menu. So we can choose between different output options depending on the cutting machine you're using. You may want to have your DXF curves into splines and lines, or into polylines, or arcs and lines. We can also change the DXF seam allowance. The seam allowance is an offset of the pattern. So in some cases you may want to have a seam like this, and in some cases you may not want that. So basically we can set that number to 0. And that way, when exporting your file, you won't be getting that offset. So you can import it back. and now we're not having that seam. We can see that also it has imported all these features and all these curves separated by layers. You can add features, tags to your parent piece, so that gets exported along with the XF file, and that will be organized into layers. So whenever you import it back to any other CAD software or CADing table, you'll get it organized by color in different layers.